Hi, I'm Tanner, and welcome to my Mach-O format series. In these videos, I'll go into detail on each part of the Mach-O format, and along the way, we'll program a tool that's able to inspect these files. In order to grasp the content of this series, I recommend you have a good understanding of C++. If you don't know any C++, you should at least have a solid foundation in programming. Anyway, without further ado, let's begin with a short introduction. Mach-O is the format that Apple operating systems use to store executables, libraries, and other types of information. DYLD, or Dynamic Link Editor, is the part of Apple operating systems that is responsible for loading, linking, and executing Mach-O files. DYLD's source code is publicly available and can easily be found with some Googling. If you wish to do a deeper dive on any of the topics covered in this video, that's a good place to start. Since we're going to be working with file parsing, let's start out with a basic class that will read data from a file. Taking a look at this header file, we have some methods that deal with managing a file handle, a method that tells us the file size, and the rest of these methods here are responsible for reading data. This template method read is able to read any data type or structure into memory, and these methods here are simply wrappers around the read method to read 1, 2, 4, and 8 bytes of memory respectively. I won't go into the code for the reader class because it's not really in the scope of this video, but for anyone who's interested, the source code will be available. The first piece of a Mach-O file is the magic number. The magic number is located in the first 4 bytes of the file. There's nothing magical about the number, it's simply a random 32-bit value chosen by the developers. The magic number confirms that the file is a valid Mach-O file and we can proceed successfully. Let's begin by writing a simple program to read the magic number of an input file. We instantiate a new reader class and call the openFile method. Our main function has 2 parameters, argc and argv. Argv contains an array of the command line arguments used to run the program, so the first element in the array will be the path to the executable. Since I'm working on a Mac, this program will be a valid Mach-O file, so we'll just feed it into itself for our tests. OpenFile will return true if the file was successfully opened, and false if there was an error. If no error occurs, we read the magic number and print it to the terminal. Here's the resulting output. We'll talk more about this number later. Although the majority of modern systems conform to a little endian byte order, Mach-O supports both the little and big endian byte orders. The endianness of a Mach-O file is reflected in its magic number. If the magic number is in the reverse byte order than expected, DYLD will swap the byte order of each subsequent memory read. Here are a couple functions that we can use to swap byte order. If you're not familiar with bitwise operators, this code probably doesn't make any sense. It's actually quite simple though, it just extracts each byte and then reconstructs the number in reverse order. Although most instruction sets provide built-in ways to swap the byte order of a number, C does not provide any functionality to achieve this natively. C++ introduced std byte swap in C++23, but for compatibility's sake, we'll stick with these functions for now. Compilers with optimization enabled will swap out this chunk of code for those built-in assembly instructions we talked about, so don't bother trying to optimize these functions. The magic number FEEDFACE signals the presence of a Mach header. On 64-bit architectures, this number is FEEDFACF. The Mach header has a few different purposes. First, it reports the instruction set that the code was compiled for. Second, it defines the file type, such as a relocatable object, executable, dynamic library, etc. Next, the header details the load commands. We'll talk more about these later. Finally, it provides some information to DYLD regarding memory privileges and linking information, among other things. This macro here compares a value to all possible Mach header magic numbers and tells us if the input is a valid Mach magic number. Let's modify our program to read in the Mach header. Notice that the only difference between the 32 and 64-bit version of the Mach header is that the 64-bit version has this extra field at the end. This value actually serves us no purpose, so we can just read in a 32-bit Mach header to cover both cases. Here is the updated code and the resulting output to the terminal. Now that we can successfully read the Mach header, let's try and make some sense of it. We'll start with the instruction set. I will use the terms instruction set and architecture interchangeably from now on. Our Mach header has 2 fields of interest, namely the CPU type and the CPU subtype. Right now, we're only interested in the CPU type. This will tell us roughly which processor the code was compiled for. The CPU subtype contains more nuanced information about the architecture, but its purpose goes beyond the scope of this video. Here are some macros defining the Intel and ARM instruction sets. For the sake of time, this project will only support these two, but there are more possible values for the CPU type. If you wish to learn more about it, you can look at DYLD's source code. Given these macros, here's another chunk of code we can use to transform the CPU type into our own data type. We now have everything we need. Let's update our main function to utilize this new code. We read in the Mach header and feed the CPU type into our newly defined function, convert it to a string, and print it out. Here's the result that we get, and it checks out, given that I'm working on an ARM64 MacBook. The Mach-O format is able to support multiple different instruction sets at once. This is accomplished via the FAT format. Each separate Mach-O file is combined into one, and a new header, called the FAT header, is placed at the beginning of the new file. Here are the data structures associated with the FAT format. Here we see the magic number and its reverse byte order variant. Next is the FAT header definition, which just contains the magic number and an integer defining how many architectures are present. After the FAT header, we have these FAT arc data structures. The field we're interested in here is the offset. This value gives us the file offset of the Mach header associated with this architecture. After adding a couple compiler flags to our build settings, the program will now compile for multiple architectures. Let's modify our code to read a FAT header. We start off by reading the FAT header into memory. However, this time our magic number shows up in the reverse byte order than expected, so let's make sure we account for that by swapping the byte order of our memory reads. We'll print the data fields from our FAT header. The FAT arc structures are stored immediately after the FAT header, so we'll read those into memory as well. Next, we'll loop through each FAT arc, swap it if necessary, and print its data to the terminal. Running this program, we see the results here. Now that we have a basic understanding of these two header formats, let's write a class to perform our analysis. We'll start with this data structure. Right now, it only contains the architecture, but we'll expand on this as we get deeper into the format. Here we have a static method that we can call to analyze a file. It takes in the path of the file, a reference to a vector of analyses, and a pointer to a string that reports any error that may occur. The function returns true or false depending on whether the analysis succeeded or failed. Jumping into the code, we clear the analysis output vector in case there are any elements inside. We instantiate our reader class and make sure that the file is opened successfully. Next, we read the magic number and determine if the magic number corresponds to a header structure. If we have indeed found a header, we'll perform the analysis and return true. Now let's take a look at the perform analysis method. We check the magic number again to determine which header we're looking for. In the case of the Mach header, we'll call this new function called analyze Mach object and add the resulting analysis to the output vector. In the case of a FAT header, we loop over all the architectures and call the analyze Mach object method on each individual Mach header. And here's the analyze Mach object method that we've been calling. Right now, it simply reads in the Mach header, swaps it if necessary, and provides the architecture based on the CPU type. This code should all be very familiar, as all we have done is abstracted the functionality that we've been playing around with so far. Jumping back to our main function, let's utilize this new analyzer class that we've just created. We'll have the program perform an analysis on itself and report the supported architectures. Looking at the result, we find the same results that we got earlier when inspecting the FAT header. Now that we've ensured the FAT header is properly handled, I'll remove the compiler flag so we're not wasting time compiling for multiple architectures. Now that our code is written in a more structured manner, let's move on. Immediately after the Mach header, there is a collection of small data structures known as load commands. Each load command begins with two data fields. The first field is an identifier that tells which command we're dealing with. Next, we have the size field, which lets us calculate the location of the next load command in the file. This data structure does not actually include any information about the command, since each load command actually has its own data structure. But for the purposes of simply iterating through all of the commands, this is all we need. So now let's update our analyze Mach object method to loop through each command. The location of the commands begins directly after the Mach header, and they are stored contiguously in memory. So we'll initialize our command offset to right after the mock header. For each command, we'll call this new method process load command and then return. Inside the process load command method, we begin by reading the load command into memory. We take note of the command's size. If the size is 0, we know something went wrong, so we'll report an error. Otherwise, we'll just add the size to the command offset so it points to the next command. Notice that the command offset variable is a reference, so we're actually updating the offset in the scope of the analyze mock object function. For now, we'll just print out the command identifier and its size and return. And here we have the terminal output. That's all for this video. In the next part, we'll go into detail on the load commands, memory regions, and more. I hope you learned something valuable, and if not, I hope you at least enjoyed this introduction to the Mach-O format. Thanks for watching, and I'll see you in the next part.